Right. So in the previous class, we talked about the dominance property. We talked about uh, three by three matrix, I guess. Yeah, three by three matrix, and we talked about the way you can remove the unnecessary or not so important columns and in rows. It's actually the removal of the not so promising outcome, so that you have a fruitful outcome. Generally, we curtail it to 2 by 2 matrix, right? Then we solve and we finally got our value of the game. And this is pretty cumbersome, so we have devised an approximate method when which you have a decision rules, so in which you have to uh, manipulate this particular 3 by 3 matrix into 2 by 2 depending upon the decision rules or something like that, right? And it also yields a fruitful value, which is the same optimal value of the game, right? Now in this lecture, what we're gonna do is we're gonna focus on the game theory, but a concept which we have learned in the module number one. It's called linear programming problem, right? So you don't have to really do trial and error, but instead you can use Dual-Simplex to find out the value of this game, right? So I'm gonna replicate the same problem, which we consider for dominance property. So just replicated player A and player B, and which have got the rows and columns. It's a 3 by 3 matrix, right? Then what we do is the row wise we will name it as x1, x2, and x3. So x1 is row 1, x2 is row 2, and x3 is row 3. And y1 is column 1, and y2 is column 2, and y3 is column 3. So this is how the nomenclature, or we will provide label for our matrix. Dual simplex model, you probably know what is a primal. Primal is the exact problem, and dual is the opposite of that. Say, for example, if the primal is a minimization, then dual is a maximization, and vice versa, something like that. So the first, say, the entire matrix, we will be converting into the objective function by since it is a maximization, we will be going in terms of the column wise. So we put y1, y2, and y3. So we'll maximize y equals to y1, y2, and y3. Then the constraints, like the constraints are the column wise, like 1, y1, then 2, I mean 7, y2, then 2, y3, less than equals to 1. So this is the constraint. Then 6y1, then 2y2, and 7y3 less than 1, and 5y1, 1y2, and 6y3 is also less than equals to 1. So these are the constraints, structural constraint, and all y1, y2, and y3 are greater than equals to 0. So non-negativity restriction. So this is what we generally do in linear programming problem. But in addition to that, in a objective function, y equals to y1 plus y2 plus y3 equals to 1 by v. So we'll talk about this little later. 1 by v is the value of the game. So it is equals to 1 by. To solve this problem using linear programming or simplex method, in fact. And the solution is, we don't go into linear programming solution, but many of you know how to solve problem, I mean linear programming problem using simplex table. So the answer is y, which is the objective function, which is 0.25, where y1 equals to 0.125, and y2 is 0.125, and y3 is 0. So y1 represents column 1, y2 represents column 2, and y3 represents column 3, right? So that's why it is 0, and it has some value, and we have got y. And we can find the value of the game, which is equals to, or 1 by value of the game equals to y. So if you find, if you want to find v, it is 1 by y, right? So y equals to 1 by v, so v equals to 1 by y. So we know what is the value of y, it is 0.25. So value of the game is 1 by 5, which is 1 divided by 0.25, which is 4. So the value of the game we achieve is 4, and y1, y2, y3 are the same. But it is not probability p1, p2, or I can even say this is p3. But instead it is y1, y2, and y3. From that we can find out the value of it is actually Q1 and Q2. For B, it is Q1. For B2, it is Q2. Remember the formula which we calculate in the dominance property, right? Say in the dominance property, let's go to this thing. We use the formula for Q1. So Q2 is 1 minus Q1. So this thing, the value of the B1 and B2, we have found it using, linear programming problem, right? Say this and this. Let's see whether we get 0.5 and 0.5 or something like that. All right. So I'm just go back to linear programming problem, right? So we have got y1, y2, and y3, but we need to find q1 and q2. So q1 equals to, so this is very important, it is v times y1. I repeat, q1 equals to the value of the game multiplied by y1, so that is 0.5, and q2 equals to, you can take 1 minus q1, right? So q2 is 1 minus q1, or you can even take value of the game multiplied by y2, that is 0.5. Both have the same value, and this thing which is probably discarded from the original thing, which is b3. So which means we are removing this thing. So from LPP we understand that, so this particular thing gets removed or something like that, right? So that's the analogy using primal. So this is the first part, like we need to do dual to find out the value of p1 p2, which is the value of a1 a2 and a3, something like that, and both the cases you get the same value of the game, right? So that's a very important significant feature of this LPP, right? So the dual, so we talked about primal, which is a maximization problem, in which we have got y1, y2, and y3, and we take the row wise, like 1 into y1, 7 into y2, and something like that, right? So we define y equals to 1 by v, right? The next is dual. Dual will be looking into minimization case. So instead of y1, y2, y3, we'll be taking x1, x2, and x3. Say this time we'll take this a column wise. Like for example, in the objective function, x equals to x1 plus x2 plus x3, which is equals to 1 by u. This is the objective function in dual. Then the constraints are 1 into x1 plus 6 into x2 plus 5 into x3, and this time it is greater than equals to 1. Say this is a standard minimization case when which your constraint should be greater than equals to constraint, right? So that's why we have got greater than equals to 1, whereas in the primal problem we have got less than equals to 1 for all these things. And then non-negativity restriction, x1 greater than 0, x2 greater than equals to 0, x3 greater than equals to 0, right? So this is typically important conversion of our given problem in terms of its dual, right? So when you solve your dual, x also is the same because it's a value of the game, 0.25. So u equals to 1 by x, it is nothing but 1 by 0.25 is 4, and x1 equals to 0.10, and x2 equals to 0.15, and x3 equals to 0, right? Next we can find out the value of this, actually p1 and p2, and you can see that x1, x2, and x3 is 0, which means the row 3, it is 0, right? So this is typically u multiplied by x1, so which is 4 multiplied by 0.1, it is 0.4, then 4 multiplied by 0.15, it is 0.6, or you can even take 1 minus 0.4, which is p1 is 0.4, 1 minus 0.4 is 0.6. So in either cases it is correct, right? So then finally it is 0, so which means that we have removed a3 and b3, so which means that we have removed a3 and b3. So 1762 is the curtailed ideal 2 by 2 matrix, so that is optimal results of 4. The value of the game is 4, and this is typically the same process in terms of linear programming problem, right? Right. So I just quickly repeat. So in the dominance property, we talked about the problem, and we have looked into all the 9 options, And then we have also developed an approximate methodology, and we have solved that using the decision rules, standard decision rules. Then we yield a value that is more optimal in this case. Then we all can also saw how to solve the problem using linear programming problem. And this is the formulation. We use the dual simplex method. Initial problem gets converted, gets solved using the maximization case with b1, b2, and b3, which is y1, y2, and y3. So objective function y, capital Y, equals to sum of all y1, y2, and y3, and it is equals to 1 by p. And structural constraints in terms of row wise, like 1 into y1, 7 into y2, and 2 into y3, less than equals to 1, since it's a maximization case. And we have solved this problem. We got value of objective function and also the decision variables y1, y2, and y3. And from the objective function, we'll invert it so that we get the value of the game, which is v equals to this. And we don't do anything to y1, we just directly put that. Then we can find the probability of P1, the column 1 realization, which is nothing but value of the game multiplied by y1. For Q2, it is value of the game multiplied by y2. And this thing, it is, since it's 0, so there's no effective. So value into that effective will, ineffective value will become 0. So which means that we have to remove B3, which is third column, right? So that's how this is a part one. Then we'll find out dual to the corresponding primal. So dual will be a minimization case, and instead of y1, y2, and y3, we'll be taking x1, x2, and x3, and that is equals to 1 by u, which is also a value of the game. Then we talked about 1 x1 plus 6 x2 plus 5 x3, and in this case is greater than equals to 1. Then the non-negativity restriction. Then we get the value of x1, x2, and x3 and objective function. So in this case, x3 equals to 0. So which means a3 is removed, which is the third row. So that's how we got the optimal value and the value of the game, right? So this is typically another method, but I've just hidden the procedure for solving this using simplex method. So it looks simple, but when you do with the simplex review, then a lot of iteration happens, and this is kind of a pretty lengthier problem. But if you use some computers in a real life scenario, when you have many numbers of variables or decision making, say 10 by 10 matrix, like in the case of digital assignment number 3, or 20 by 20, 50 by 50 matrix, then you can probably use computers for solving this particular game theory using linear programming approach, right? So this is another approach.